In this work, we present LOCC, a cutting-edge approach to open vocabulary occupancy prediction. Open vocabulary occupancy prediction facilitates predicting the occupancy with arbitrary sets of vocabularies using only unlabeled image LiDAR data for training, which is crucial for applications such as autonomous driving and robotic navigation. Due to the lack of large-scale occupancy datasets with language annotations, distilling knowledge from vision language models into occupancy prediction networks presents a viable solution. Previous methods either use image features from the pre-trained vision language models as intermediates or treat voxels as point clouds and assign semantic labels to them by model view projection. However, the feature values of objects with the same semantics may vary, as image features inherently encode both semantic and appearance information, leading to inconsistencies in semantic representations across different inputs. Consequently, the pseudo-labeled ground truth derived from image features is inherently noisy in terms of semantics, failing to provide precise guidance for voxel-level understanding. For model view projection, it overlooks the occlusion problem and only uses single-frame images, leading to coarse voxel-to-text correspondences. To address the aforementioned issues, we revisit the core aspect of OVO, generating dense and fine-grained 3D language occupancy ground truth. In this work, we propose a semantic transitive labeling pipeline to achieve this goal, without laborious procedures. It can be roughly divided into two steps: label transferring and scene reconstruction. For the first step, we use large vision language models, LVLM, and open vocabulary segmentation models, OVSEG, to assign text labels to each pixel, obtaining consistent semantic representations. Then, through the projection of LiDAR points, the text labels are transferred to the LiDAR points, bridging the gap between 3D data and texts. In the reconstruction process, we model the occlusion relationships of the point clouds during point projection, preventing the wrong label assignment of voxel-based model view projection. With the pseudo-labeled LiDAR data, we reconstruct a temporally dense scene by merging multi-frame LiDAR points to obtain a dense 3D spatial representation. Furthermore, to reduce the impact of segmentation noise from individual frames, we apply majority voting voxelization to assign the most frequent label to each voxel. The resulting ground truth enhances 3D language supervision for open vocabulary occupancy networks. Here, we provide an example of the conversation process with QuenVL to extract vocabularies from an individual image. Here, we show some comparison results for our generated pseudo-label. Benefiting from the generated pseudo-labeled ground truth, we can use it to train OVO models by simply replacing the conventional head with a geometry head and a language head. We validate our framework on several mainstream approaches, referred to as LOCC-BEV-Former, LOCC-BEV-DET, and LOCC-BEV-DET-4D. To efficiently align high-dimensional clip embeddings, we devise a language autoencoder that maps them to a low-dimensional latent space, reducing computational cost. Here, we show the qualitative results on the OCC 3D new scenes test set. LOCC outperforms all competing methods in terms of MIOU, demonstrating its superior performance. Here, we present detailed metrics for the pseudo-labeled ground truth generated from different OVSEG models. Here, we present some visualization results. In a word, in this work, we have proposed a novel open vocabulary occupancy prediction method, named LOCC. Extensive experiments demonstrate the effectiveness of LOCC on the public datasets. Thanks for watching.